Okay, so if we're talking about momentum, then as we've generally stated, talking about it as a class, momentum is the idea of a object with mass moving at some velocity. Okay, and because velocity is a vector, I can move north, south, east, west, in, out, whatever direction. Like you can point in a direction for a vector. When we think about momentum, it is a mass and a velocity, so that momentum vector needs to be a vector. It can't just be a number. It can't just be a scalar value. It has to have a direction. So for momentum, the equation that we'll use will be a mass multiplied by a velocity. And this is where things get interesting. Momentum begins with the letter m. So you might think we'd put a letter m here for the left side of the equation, but don't do that. That would make sense. And physics is weird. And we've already used the letter m for mass, so we're like running out of letters, people. In physics, we actually use the letter p for momentum. And it's a lowercase p with the arrow vector on top of it. So it's a lowercase p as a vector. So we put that little symbol, that little arrow vector on top. I know that's super weird, but that is what it is. So this is what we have in terms of our equation for momentum. We have that momentum, p, equals mv. So an object with mass moving at a velocity has some momentum. We just multiply those terms together. And whatever direction the velocity is in, if the velocity is moving this way, that is the same direction for our momentum vector. It could be a little bit longer because we're multiplying it by a mass. Could be a little bit shorter, but it is in the same direction as that velocity vector. Okay? So they will be the same there. Now, something that we haven't talked much about is the idea of how to get an object moving. When we were in kinematics, we were talking about like projectile motion. We just said an object has a velocity. It just has it. Don't worry about how it got it. It just has it. Now, we're going to concern ourselves with how objects gain a velocity. If a small toddler runs up to you, down from the preschool wing, I don't even know if they're here, but if a small toddler runs up to you and tries to push you, they are super weak. They have not hit the gym yet. So when they go to push you, that is not a lot of force. On the other hand, if these guns come up and give you a shove, you're going to go flying because I'm super, super strong. Okay? Or if you've ever played a sport like baseball, tennis, golf, one of the things they tell you is to follow through with your swing. And there's a very important reason with this. Not only when you swing are you applying a force on an object, but when you follow through with your swing, you're applying that force on the object for a longer period of time. If I push someone longer, then I can get them to move faster. Think of it this way. You sit down on a cart or like a skateboard, I stand behind you, and I run and push you down the hallway. If I can exert force on you, and I do that force for a longer amount of time, I can speed you up. It's the same idea with if you're sitting in a car. If you slam down the gas pedal, your car is going to accelerate with a lot of force, but you only do it for a fraction of a second, you're not going very fast. Because you only did it for an instant. You're like, bam, nothing. On the other hand, if you slam down that gas pedal and you hold it there, your car is going to start speeding up a lot more, and you're going to get to higher speeds. Higher momentums, because your car has a mass. This ability to apply a force on an object for a period of time to change the momentum of the object, we call that an impulse. So an impulse is equal to the idea of a force, F, with a vector, multiplied by some amount of time, t. Now, since the force is a vector, impulse must be a vector as well. And since impulse starts with the letter I, we're not going to use the letter I for impulse, because that would make sense. And as we're seeing here, nothing seems to make sense. We instead are going to use the letter J. The letter J is used for impulse. There's an ongoing joke each year where my students say, why don't we just call it Gympulse? Because the letter J is there. I don't know, okay? It's just like ancient Greek stuff. We run out of letters here. But that's what is being represented here, okay? So if you're able to apply a force on an object for a longer period of time, a force multiplied by a time will give you an impulse, and that impulse can change the momentum of an object. As such, what we actually see here is that our impulse is equal to a change in momentum. And what we mean by this is an impulse here, which we could write as J. This will have to be equal, as we already know, to F times t. But if the impulse is equal to a change in momentum, this also has to be equal to a change, which, if you recall, we use the triangle, the delta symbol, to represent a change in something or a difference. So this is a change in momentum. And for a change in momentum, what we're really talking about is a final momentum minus an initial momentum. A delta is always equal to a final minus an initial. So we can say here that this is equal to whatever the final momentum is minus whatever the initial momentum is for our object. So if a hockey puck is stationary, it's not moving, it has zero velocity, its initial momentum is 0. If you take a slap shot and you slap the puck, it's knuckle puck time. You've applied a force over time to the puck. That's an impulse. Now the puck has gone from stationary to moving. With some velocity, it has some final momentum. What we can actually do here is we can rewrite this equation in a slightly easier form to use. We can just say that the force multiplied by time is going to equal, and then what I'm going to do is I'm going to take this impulse here, these PFs and PIs. I know that an impulse is a mass multiplied by a velocity. And if the mass is remaining same for something like our hockey puck or a baseball or whatever, then I can pull it out of the equation, and I can say this is equal to a mass multiplied by a final velocity minus the initial. So we just did a little bit of math to clean up that equation. But this equation right here, the impulse is equal to a change in momentum, m times the quantity Vf minus Vi. That is a very important thing that we're going to be using throughout this unit. It'll show us that if we apply forces at times onto our objects, we can get them to change their velocities. Okay? And that idea of a velocity is very important, as we're going to see in the upcoming example in the next video, because velocity is a vector and it has a direction. So until then, that's where we're going to hold this. In our next video, we're going to take a look at this example of a baseball player here, but these are the equations we're going to need. Please make sure you ingrain those into your brain. But right now, we are finished.